discuss about batch normalization. So this is very important concept to understand. Okay, so let me draw the diagram and explain the concept to you. So there are basically two inputs, and similarly here Z2 function of Z22, right? So the output is A1, right? Again here Z21 function of Z21, A2, here Z22 function of Z22, and then this will be the output, right? So let me explain this diagram first. So here we have two hidden layers, right? We have two hidden layers over here. One input layer. Basically, there are two input neurons, right? And here there is the output, right? So here there is one hidden layer, and here there is the second hidden layer, right? So what will happen in this training, right? So the first data will be feed forward, right? So what is feed forward? Here we have two inputs, X1 and X2, right? So that we get W1X1 plus W2X2, right? W1X1 plus W2X2, right? So what is this equal to? This is nothing but Z11, right? So yeah, so let me mark that. Clear now? So what is the Z1 actually? Z11 actually, right? So this is actually Z11, right? Z11 is nothing but W1X1 plus W2X2, right? So we will be getting that actually over here. After that, Z1 value is sent as input to activation function, right? So what is the activation function output we get over here? A1, right? And similarly for here, A2 is the activation output, right? Now these A1, A2 will be the inputs to the next hidden layer, right? So this is how it repeats until the last layer, right? So this is clear, right? So we have two inputs, X1 and X2, and let us take this X1. So it is here what will happen? We will be getting Z11 as W1X1 plus W2X2. So here you can see that, right? X1, and here there will be W1, and similarly here there will be W2, right? So W1X1 plus W2X2. So that is the output over here. And then the activation function is passed. And so that there will be an output. Now the output is fed into the next hidden layer. Again, there is an activation function, right? So this is how the process will continue, right? So now let us discuss about the batches, right? Now let us discuss about the batches. So when we talk about batches, let me say that batch 1, batch 2, batch 3, batch 4, batch 5. Say for example, right? Say I have around 15 data points, right? So what will happen over here? Each data, so actually it will be sent to the, all the data will be sent to the batches, right? So in batch 1, what will happen? So there will be like a feed forward, what we discussed already, that happens. So there will be Z values, right? So totally how many values will be getting? So 15 Z values, say for example, right? So if there are Z11, there will be 15 Z11 and 15 Z22, something like that, right? Right. So what is happening over here? We are calculating Z's. Z's are being calculated over here. What is the next step? In the next step, mean and variance are being calculated, right? Mean and variance are being calculated, and then it is being normalized, right? And then it is being normalized. Clear? Now, what will happen? Now, the next step is that, like here, the data will be having 0 mean and 1 standard deviation, right? So we know about normalization, right? So 0 mean and 1 standard deviation we get, right? So now what we are going to do, like we will be having these values, right? So these will be actually NIs. So now what are we going to do over here is we are going to scale and shift using alpha and beta values, right? So this will be done scaling as well as shifting using alpha and beta values. So if you look into this, Zi cap is equal to alpha into Ni plus beta, right? So what is this Ni? That is what we discussed, right? So we get all the values and that are actually Ni's. So why do we, so let me show you like how does the scaling and shifting looks like. So once you do this, scaling, this is how the data will look like, right? So what is happening over here? Mean, okay, so let me draw this, right? So mean 0 and standard deviation 1. Now what are we going to do that? Like just we are shifting it now, right? So what are we doing now? We are just shifting it, right? So we will understand that in shortly, right? So what is happening over here? After scaling and shifting, it will change its variance, right? Okay. So now let us understand why shifting. Why shifting? Because we know very well that the output from an activation function is non-linear, right? So if we normalize mean 0 and standard deviation 1, then we will lose that non-linearity. Am I clear? The output from activation function is always non-linear. If we normalize with the mean 0 and standard deviation 1, we may lose that non-linearity. So here I am talking about alpha and beta, right? Alpha and beta. So what are these alpha and beta? So who will identify that? Actually, the network identifies alpha and beta. Same way like how we were updating weights based upon the loss function. So we are adding one more layer, that is batch layer. We will be updating alpha and beta, right? So to get minimum loss, what alpha beta should be there, right? So that is decided by the network. So in order to speed up the network, the convergence of weights each batch we need are D players C input from same distribution. So each batch should have same distribution, right? So that the convergence may speed up. So it is not necessary that it should be with the zero mean and one standard deviation. So it is not necessary to be with the same distribution. It can be of in, right? So let me explain in simple way, right? X11, right? Sorry, let it be X1, sorry. And here again, right, let it be X2, right? So I may have it like Z11, Z12, right? So here each Z11 we use alpha and beta, right? So like here you can see the two neurons. So how many alpha and beta we use? So N alpha beta, right? So for each Zi we have one alpha and beta, right? So let us so here what we have seen is like right. So what does this batch normalization do? So this improves the gradient flow through the networks and it allows higher learning rates. And then it reduces the strong dependence on initialization and it acts as a form of regularization in a funny way and slightly reduces the need for dropout, right? So you can see about this mini batch mean, mini batch variance, normalize, scale and shift over here, right? So like it is clear, I guess, right? So this is what the batch normalization does.
Let us discuss about batch normalization. So what is meant by batch normalization? Normalization, we must have some idea. Batch, we know what is meant by batch. So let us try to combine together and try to understand what is batch normalization. So before dive deep into the concept of batch normalization, let us try to understand what is normalize and standardize. So what is meant by normalization? So just think that I have a feature for income which is ranging from 10 to 1000. So what I'm doing here is I'm trying to normalize into the scale of ranging from 0 to 1. So what I'm doing over here, from 10 to 10,000 values, I'm making it to change to 0 to 1. So this is called as normalization. What is meant by standardization? Z-score. We have heard about it, right? So Z-score is equal to X minus mu divided by sigma. What is X? X is nothing but the corresponding value. What is mu? Mu is nothing but the mean. Sigma is the standard deviation. So this is the basic difference between normalize and standardize. So what is meant by normalization? So normalization is a data pre-processing tool which is used to bring the numerical data to a common scale without distorting its shape. That is what I said, like changing the income from the values ranging between 10 to 10,000 to 0 to 1. So when we input the data to a machine or deep learning algorithm, we tend to change the values in a balanced scale. So why do we do that normalization? If we do not do that, what may happen? So what we have studied in machine learning algorithms are, if we do not normalize the data, if we do not standardize the data, what we can expect is sometimes that particular the magnitude of the values may be different. So in that case, we could expect some bias in the solution. To avoid that, we always do normalization or standardization, right? Okay, so what is meant by batch normalization? So now we are studying about the neural network. So here we feed lot of inputs to the neural network, right? So actually, before passing it to the network, all the inputs have to be normalized, which means we try to change the inputs to have zero mean and unit variances, right? So the inputs should be decorrelated. So what will happen over here is it will reduce the amount of change in the input distributions to the hidden layers during training. So this will reduce internal covariate shift. So what is meant by internal covariate shift? That we will be seeing shortly, right? So what I'm trying to say here is the inputs to a neural network should be always normalized before passing it to the network. So we transform the inputs to have a mean 0, right? That is what I said. We transform it to have mean 0 and the variance or standard deviation is equal to 1, right? So during training, the changes made to the parameters of the network after the distributions of the activations in the network. So the hidden layers of the network are forced to learn constantly shifting input distributions so that it decreases the rate at which the network learns. So it also reduces the amount of change in the input distributions to the hidden layers during training. So that is why I said it will reduce internal covariate shift, right? That's why I said it will reduce that. So I'll be telling you what it is, right? So let us also try to understand how does this batch normalization basically work. So what do we try to do over here? We try to normalize each of the hidden layer input, right? So that they are decorrelated, means they have zero mean and unit variance, right? So this is computationally expensive, right? So therefore, some simplifications are made over here. So what do? Each scalar feature is normalized independently to have zero mean and 1 unit variance, right? So each dimension of the feature vector is normalized as follows. So you can see that X, right? So this is basically like a normalized feature value, right? So this is basically normalized feature value for kth dimension, right? And similarly, this one, this mu is basically mini batch mean for the kth dimension. So what is this? This is basically mini batch mean for kth dimension, right? And similarly, this sigma square is, we all know that sigma square means variance, right? So this is mini batch variance for kth dimension, and this is basically the smoothing term to prevent a division by zero, right? So here the features are not decorrelated in batch normalization. Clear? Right? And as we normalize each input of a layer may change, what the layer is able to represent, the parameters gamma and beta are being added, right? That is being added. So this is what we are going to understand now. So for each dimension, the parameters gamma and beta are able to scale and shift the normalized value such that it is optimal. So let me write that y. This is equal to gamma. So you will understand everything shortly. Just be patient. When I write this, you may it may look complicated, but it is not going to be complicated. I'll make it so simple. So here the parameters gamma and beta are updated during back propagation such that the loss of the network is minimized, right? So another thing what you have to understand is like mini batches are not used during inference. An alternative technique is used to normalize the activations of the network. So during training, the moving averages of the training sets mean and variance are computed. These statistics are used in order to normalize the activations of the network at test time. So these are the steps for the normalization, right? So I can rewrite it as which is equal to, which is equal to x. So what I'm writing here, just make a note of it. I'll explain what it is. Divided by square root of what I'm writing now, variance, right? Okay, so here again, this is going to be the same. So let me tell you what is what. So x, this is basically the feature value, and this is basically the training set mean, and this variance x per k is the training set variance, and this is basically the smoothing term, right? So this is nothing but the normalized feature value, and this is nothing but the output of the batch normalization, right? So you may also have a question that why batch normalization enable the use of larger learning rate. So here we use a large learning rates. It will result in deep networks. We all know that the use of large learning rates will result in exploding or vanishing gradient. It may also result in the network getting stuck in local optima, right? So batch normalization addresses these issues. So the activations of the network are normalized. It prevents small changes to the parameters from being amplified into suboptimal changes, right? So when we update the weights in proportion to the learning rate, so the use of a learning rate may lead to exploding gradient. So however, it is not a concern when we use the batch normalization, right? So here the scale does not affect the layer Jacobian nor consequently the gradient propagation. This is what the research says, right? So the scale that is being referred to is called as the learning rate, right? So we also have to understand how does this batch normalization regularize the model, right? So every sample in batch undergoes a transformation that is dependent on the batch mean and standard deviation. So the appearance of a given training example to the network is dependent on the batch it is in. So this prevents the network from producing deterministic result for any given training example. So this is found to improve the generalization capabilities of the network, right? So this I have given a overview about batch normalization. Let us try to understand in detail with a little more concepts, right? So we all know that what is normalization. So basically we are trying to bring the numerical data into a common scale without distorting its shape. This is what I told, right? Okay. So now let us try to understand what it is, right? So we are saying batch normalization. So what is meant by batch? So batch is nothing but a typical neural network is trained using a collected set of input data, which is called as a batch. So the normalizing process in batch normalization takes place in batches, not as a single input. So how do we understand this? So look at this diagram now. You can see 4 inputs over here, right? X1, X2, X3, X4. These are the inputs over here. These are in, see, okay. So we have, just understand that we have a deep neural network. These are basically the inputs, okay. And also I can say that here L, W1, W2, W3, W4, these are basically the weights, right? So how many weights are there? L weights are there. And so I can say that number of layers. L stands for the number of layers. And here the activation function used is sigmoid. Okay. So now initially our inputs X1, X2, X3, X4 are in normalized form because they are coming from the pre-processing stage. So when it crosses to the first layer, it transforms as a sigmoid function applied over the dot product of X and weight matrix W. So what we get over here, what I'm trying to say over here is H1 is equal to sigma W1 X. So what I mean over here, sigma, we know what is sigma and what is weight, what is input, right? So similarly, this transformation will take place for the second layer. Yes, I'm clear, right? And then it will go on. This process will happen in second layer, third layer, fourth layer, fifth layer, and finally happens in the last layer. So, right? So here the input are actually normalized with the time. So the output will no longer be on the same scale. So as the data go through the multiple layers of the neural network and L activation functions are applied, it leads to an internal covariate scale, covariate shift in the data. So this is what I said I'll be explaining shortly, right? Covariate shift, I'll be explaining shortly. Before that, we will understand like how does this batch normalization basically work, right? So normalization, we know it is the process of transforming the data to have mean 0, 0 mean and standard deviation 1. So we have some input from layer H, okay? So what are we going to do over here is basically, this is basically the input and we are trying to find out the mean of it, right? So what is this basically? We have our input, we have our batch input, okay? We have our batch input from layer H. We need to calculate the mean of this hidden activation, step 1. The next step is that once the mean is being calculated, the next step is to calculate the standard deviation of the hidden activations. So we have already the mean, right? So what is mean? 1 by n summation hi, right? So we already have the mean now. So what are we trying to do? We know that, right? This is what, right? So what are we trying to find out now? We have the mean and standard deviation already ready. So based upon that, we are trying to get this, we are trying to calculate the standard deviation, right? So what I'm trying to say is mean and standard deviation should be ready. So already we have calculated the mean from the previous step. Now we are finding the standard deviation. Sigma is equal to 1 by n summation hi minus mu the whole square, right? So this is done now. Now what is the next step? Okay, so we will normalize the hidden activations using these values now. So what are we going to do? We will subtract the mean from each input and divide the whole value with the sum of the standard deviation and the smoothing term. So how can I write that? I can say that H is equal to, basically I'm going to just show you. I know that this is what minus mu divided by sigma plus epsilon, right? So let us try to understand what is this basically. This is nothing but the smoothing term, right? And what we have done, we will subtract the mean from each input. So this is basically the input and we are subtracting the mean from that and dividing it with the sum of standard deviation and the smoothing term. Hope it is clear, right? So what is this smoothing term? This smoothing term assures numerical stability within the operation by stopping a division by a zero value, right? So here the two components of the batch normalization algorithm are gamma and beta. So actually, in the final operation, the rescaling and offsetting of the input take place. Actually, two things happen over here. So one is about the gamma and the another one is about beta. So what is meant by gamma? Gamma is nothing but rescaling and beta is nothing but shifting. Right? Gamma is rescaling and beta is shifting of the vector values from the previous operations. So now we have two learnable parameters during the training neural network, right? So the optimal value for gamma and beta has to be used. This is basically gamma, right? So gamma and beta values have to be used so that we will get the accurate normalization for each batch. So whenever we study something, we should know what are the advantages of it, right? So what are the advantages of batch normalization? I can say that it will speed up the training time because by normalizing the hidden layer activation, the batch normalization speeds up the training process, right? Second one is handles internal covariate shift. So I'm saying again and again about covariate shift. So what is meant by this? So here, what will happen is we are ensuring that the input for each layer is distributed around the same mean and standard deviation, right? So let us try to understand, say for example, I am making an image classification model, okay? I'm making an image classification model. So in that, what I'm trying to do is I have a number of images and my model is trying to figure out whether the image is a cat or not a cat, okay? So I have the images of white cats only. Now these images will have certain distribution as well. So now based upon the feature, say for example, when I show a white cat, my model will predict that, okay, it is a cat. And if I show a picture of a bus, it will say that it is not a cat, okay? So this is how my model is predicting, right? Okay. So what will happen now if I get a new set of images which has non-white cats? Now what will happen? These new images will have a slightly different distribution from the previous images. So the model will change its parameters according to this new images. So the distribution of the hidden activation will also change. So this change in hidden activation is actually called as internal covariate shift. Okay. So this is what you have to understand about this one, right? So the third application is about smoothing the loss function. So batch normalization smoothens the loss function, which means it turn by optimizing the model parameters, improves the training speed of the model. So we in this video try to understand about batch normalization and its advantages. So let me summarize all that. The first point is that what will happen? It will normalize output from activation function. Let me write in some other form. So Z is equal to X bar minus mu divided by sigma. And what is the second step? It is being multiplied, normalized output by arbitrary parameter called G. See, you can say with any of the parameters. So now I'm saying that Z into G. So multiply normalized output. This is basically the normalized output by arbitrary parameter G, right? So Z into G. So the third step is that add arbitrary parameter B to resulting result, right? So basically Z into G plus B. So this is what we were studying in this batch normalization, right? So whenever we write code, we may be importing batch normalization from Keras layers. So this is the code from keras.layers import batch normalization, right? So hope this really clears out all the questions about batch normalization. And I hope you really enjoyed the session and you had a clear understanding about batch normalization. Thank you so much.